Hello everyone, welcome. For this problem, we are asked to evaluate the following indefinite integral, the integral of the square root of tangent of x dx. The first step is to make the following substitution. We are going to call u the entire integrand square root of tangent of x. This means that for du dx, after applying chain rule and noting that the derivative of tangent of x is secant squared x, we obtain the following. This means that dx is equal to the following. We can substitute both of these quantities back into the integral as such. Now at this point, we shouldn't have more than one variable in the integrand, and since we are integrating with respect to u, there should be no x's. The square root of tangent of x we can easily write in terms of u, since the square root of tangent of x is simply u from our definition. The secant squared x is not as straightforward. It would be great if we could find a way to write secant squared x in terms of the square root of tangent of x, so we could use our substitution again. To accomplish this, we're going to use the following somewhat basic trigonometric identity. Sine squared x plus cosine squared x is equal to 1. Now how does this help with secant squared x? Well, we need to remember that secant x is simply just 1 over cosine x. So let us divide by cosine squared x everywhere, and we see that sine squared x over cosine squared x is just tangent squared x, and 1 over cosine squared x is simply just secant squared x, which is exactly what we are trying to define in terms of tangent of x. We can substitute this in for secant squared x, and we are one step closer to transforming the entire integrand into the u domain. Remember, we still should not have any x's in the integrand, but at least now we have a tangent squared of x function, which we could easily write in terms of square root of tangent of x by writing the exponent 2 as 1/2 times 4. And using some properties of exponents and the fact that tangent of x to the 1/2 power is the same thing as the square root of tangent of x, we end up with the following equivalent form of tangent squared of x. This is useful since the square root of tangent of x is simply equal to u based on our definition. After substituting u in, we end up with the following transformed integral. At this point, we have an entirely new integration problem in the u domain, which when evaluated will give us the integral of square root of tangent of x as long as we convert u back to the x domain after we're done. So how to approach this integral? Well, when tackling integration problems, a good strategy is to look for portions of the integral that look like derivatives of other portions. This will guide you to make an educated substitution and proceed with determining a solution. In this case, I have a numerator of 2 times u squared and a denominator of u to the 4th plus 1. I know that taking the derivative of a 4th order function reduces it to a 3rd order function, and since I have no 3rd order functions in my integral, it doesn't seem like either of these functions can be written as derivatives of one another. Another strategy, especially when dealing with quotients, is to divide each side of the fraction by one of the terms, and then ask ourselves the same question: does something look like it could be the derivative of something else? This is the approach we will eventually take. However, this can usually only be fruitful if both the numerator and denominator have the same number of terms of distinct exponent order, and are of the exponent order that is consistent with what happens when you differentiate. In order to match the number of terms of distinct exponent order in the numerator and denominator, let us write 2u squared as u squared plus u squared. Now we have 2 terms of order 2 in the numerator, and 1 term of order 4, and 1 term of order 0 in the denominator. There is still no substitution that will help us at this point, but remember, we want to divide everything by one of the terms, turning each one of the terms into a fraction, and then try again for a substitution. Again, this can be helpful if we have 2 terms of distinct order in the numerator, just like we have 2 terms of distinct order in the denominator. Right now, both terms in the numerator have order 2. We can fix this by employing a very powerful strategy in integration, and that strategy is simply adding 0 anywhere we want. Adding 0 anywhere we want allows us to import anything we think may help, as long as we subtract it at the same time. For this problem, we will add 0 by adding and subtracting 1. This does not change the integral, and after some rearranging, we see that we end up with 2 integrals. Each one of them has 2 terms of distinct order on the top and bottom, which is a good starting point if we're going to divide things out and then look for a substitution. You might be wondering, instead of adding and subtracting 1, couldn't I have added and subtracted 2, or u cubed, or u to the 4th, or sine of u? And the answer is yes. We can add and subtract anything as long as we think it may help us write something as the derivative of something else. Experience and foresight may provide special insight on which 0 to select, but for now adding 1 and subtracting 1 is a good place to start. Let us focus on the first integral. Again, there's no substitution that can help us since the orders don't seem to conform with differentiation patterns at the moment. However, let us divide every term by u squared. After doing this and simplifying, we end up with the following. Again, we want to ask ourselves, does something in the integral seem like it could be written in terms of the derivative of something else in the integral? Let us focus on the numerator only. Let us suppose we can make a substitution somewhere in our integral that results in the entire numerator being the derivative of that substitution. We can call the numerator f prime, and pretend like f is the substitution that leads to f prime being the numerator, which by the way would be great since it would cancel out the numerator completely and make the path for finding the antiderivative very easy from that point onwards. If f prime is the numerator, what would f need to look like? Well, let us just integrate f prime and determine what this supposed f needs to be to solve our issues. Integrating f prime, assuming the integration constant is 0, gives the following expression for f, which is u minus 1 over u. So basically, it would be nice if f was floating around somewhere in our integral, because it would make our substitution very obvious and make the rest of the integral fairly straightforward. The problem is f is sort of not present in our integral, but we have a similar structure. Instead of u, we have a u squared. Instead of the minus sign, there's a plus sign, and instead of 1 over u, there is a 1 over u squared. It's almost like if we were to just square every term in our f, we would have our denominator. Unfortunately, that's not how algebra works, but what we can do is square the entirety of f, and when we do so, we can multiply everything out, and after making some simplifications, we end up with the following. If we were to now examine f squared, we see a few familiar terms, namely the u squared and 1 over u squared terms. They are exactly the same as our denominator, which means we can write our denominator in terms of f as such. And remember, f is simply the function we need to take the derivative of in order to obtain the numerator. After plugging it all in, we obtain the following equivalent form of the quotient in the integral. At this point, we proceed with the following now rather obvious substitution. We can call what was originally f, u minus 1 over u, v. This means that dv du is simply 1 plus 1 over u squared, which is the numerator. After solving for du in terms of dv, and plugging both v and du back into the integral, and making some simplifications, we end up with the following transformed integral, which was our second transformation. First, we went from the x domain to the u domain. Now we're going from the u domain to the v domain. At this point, we should be able to recognize the antiderivative of the resulting integrand, or use an integration table, and we see that we have a form that is very similar to the following integral of inverse tangent. We just have to write 2 as a squared quantity, so we could just replace 2 with the square root of 2 squared. This means that a is simply the square root of 2, and so the first integral is evaluated as such. We now move on to the second integral. We're going to take an almost identical approach. First, we will divide every term by u squared, and then once again focus on the numerator, 1 minus 1 over u squared. Again, it would be great if the antiderivative of the numerator was present somewhere in the integral, so let us call the numerator g prime, and then integrate it to determine g. After integrating, taking the constant as 0, we see that g is u plus 1 over u, which doesn't exist in the integral, but just like before, we have a similar structure. Instead of u, we have a u squared, and instead of 1 over u, we have a 1 over u squared. So let's do what we did before and square the entire quantity g, and see if we can obtain an expression for our denominator in terms of g, and after making some simplifications, we end up with the following for g squared. We see that this strategy helped us because it precipitated our exact denominator in terms of g, which we can solve for and then plug back into the integrand as such. We can now carry out a rather obvious substitution. We can call w u plus 1 over u, which means dw du is just our numerator as expected. After solving for du, we can plug both w and du back into our integral, and after making some simplifications, we obtain the following. The resulting integral can be found in an integration table, which you may recognize to be very similar to the following general integral for the inverse hyperbolic tangent. However, we first need to write 2 in terms of a squared quantity, so we could simply replace it with the square root of 2 squared. After applying the formula, we end up with the following, where c is the sum of the integration constants for both the first and the second integral. But we're not finished yet. We still have to plug everything back into the x domain, so let us plug back in all of our substitutions for w, v, and u. After doing this, we end up with the following final answer for the integral of the square root of tangent of x.